It's a pleasure to me to talk to you about aircraft loads and its importance in aerospace industry. So, in our presentation, we're going through these topics. We are going to have an introduction. I'm going to mention the importance of loads analysis. I'm going to briefly talk about airworthiness requirements, loads theory, state of art and challenges, and careers and job opportunities. I'm sure that everybody here knows that developing an aircraft is not a simple task. There are many areas that are involved. There are professionals dedicated for design, professionals that are dedicated for aerodynamic systems. There are a lot of systems in the aircraft, the operation of the aircraft, and areas that are related to the aircraft structure. Um, loads, loads analysis is directly related to the aircraft structure. And it's one of the most important stages during an aircraft development. Large aeronautical industries, for example, Boeing, Airbus, Embraer, and others, all of them, they have dedicated teams for loads analysis. There are many engineers working specifically in loads analysis. Now let's see the data exchange about these areas. Loads team will provide information for almost all areas in the industry, but the main areas are these three. You can see the stress team, the systems team, and operation. The stress team is responsible for the structural project, and the systems teams, it's a very big area because it's responsible for all systems in the aircraft, and it's divided into small sections. For example, electrical system, hydraulic systems, and many others. And the operation area that is responsible for making rules about how to fly the airplane, how to operate the airplane. So why loads analysis are so important? I'm sure that everybody here knows that flying is safe and it must be safe. And everybody here knows that it must be feasible. I had a professor in the university. He used it to say in a very fun way that to fly, we need only three things. We need angle of attack, relative wind, and money. So we should try to reduce money, but not reducing safety. Of course, aircraft must be light as possible. And as a consequence, it must be cheap. I'm sure that none of you would pay $50,000 to fly from the United States to Europe. I would not. I would pay $1,000 or $2,000 because it must be feasible. It must be, people must fly. Okay. So let's go a little deeper in data exchange, the clients of the loads team. As I've already mentioned, the stress team is responsible for the structural project of the aircraft. And to project, they must analyze the structure and size the structure. Okay. And they cannot do anything if they don't have loads that this structure must withstand. So I put there a very basic requirement that the aircraft structure must be able to support limit loads without any detrimental permanent deformation. It's one of the great amount of requirements that um, the structure must comply with. Uh, for example, there are, when I say limit loads, I'm talking about the highest loads that are expected in the aircraft service. And there are other types of loads. For example, ultimate loads, the structure cannot fail. And there are also fatigue loads. So, as I've already mentioned, the structure must be safe. And this is um, this these two teams work together. Loads team provide information to the stress team, and the stress team will size the structure as light as possible and without damaging, without not forgetting safety. The systems team, as already mentioned, comprises many other areas, smaller areas, for example, hydraulic systems, electrical systems, environmental systems, and many others. I know that when we fly the airplane, when airplane flies, when airplane um, goes through a taxi, it shakes. The airplane structure oscillates. And this oscillation, sometimes it's called vibration, sometimes it's severe, sometimes it's not comfortable. When we passenger feel these oscillations, sometimes it's not comfortable. And the devices that are part of the systems must be safe. They must withstand this structural vibration without failures. For example, display monitors must stay safe. They must remain showing information for the crew. Hydraulic lines, they must stay safe, and also electrical components. So this structural vibration must be correctly determined by the loads team, and this data must be provided, this acceleration must be provided to the stress team so they can guarantee systems will not fail. And the operational team is going to make rules about how the airplane must fly, especially concerned to maneuvers. For example, do you believe a commercial airplane is subjected to the same loads of an acrobatic airplane? Surely not. Yes, because when we see an acrobatic airplane, the maneuvers are very severe, and as a consequence, loads are more severe. So the loads team must determine a flight maneuvering envelope, and this flight maneuvering envelope will be used in determining the airplane's structural operating limitations. As an example, once I saw a video of an Hercules, an aircraft, military aircraft, the Hercules. It was carrying water to extinguish fire, and I believe they put a lot of water inside it. And when the pilot pulled the command to a pull up, the wings broke, and it was tragic. I don't know if they did not respect the flight maneuver envelope, but it's very important because the aircraft must respect it. One of the greatest efforts of the aeronautical industry is to comply with the airworthiness requirements. All technologies must comply with their specific requirements. And these requirements are made by agencies. And the two most famous agencies are the Federal Aviation Administration in the USA, the European Union Aviation Safety Agency, and other countries have their agencies, and sometimes they have their specific requirements of because of their particularities. And if I want to sail my aircraft, if I want to make money with my aircraft, I must comply with airworthiness requirements. I cannot project my aircraft the way I want to. I must respect these requirements. And now let's see how the loads team is guided by these requirements. But Before that, we must define two types of loads. We have external loads and internal loads. The external loads are loads that are applied in the aircraft by another body, another something that is outside of the aircraft, for example, the air, gusts, when the aircraft touch down during landing, the runway applies loads in the aircraft. So these are external loads. And external loads will lead to internal loads throughout the airframe. Internal loads may be roughly defined as loads that a structural component applies in another component, or a component section applies in the adjacent section. When I say loads, I say forces and moments. There are some components are more subjected to forces, others are more subjected to moments. And how these loads are determined. Which are the magnitudes of the external loads? They are specified by airworthiness regulations. Airworthiness regulations will guide how will state the conditions that engineers must consider to determine how high external loads must be. For example, regulations state are the speeds of the aircraft during landing, vertical and horizontal speeds. For example, gust intensities, gust shapes. Regulations say that design my aircraft to withstand gusts with certain severity. And internal loads are determined by loads theory, and this is all the engineering task. Um, this is called color triangle, color triangle of loads. Loads have three big areas. Uh, they are inertia forces, aerodynamic forces, and elastic forces. Inertia forces area, um, it's more the airplane is treated as a particle for um, in case of displacement, and also we have rotational motion. So they are driven by laws of motion, and the subject is commonly treated in vectorial mechanics disciplines. The aerodynamic forces area is when a body is subjected, when a body is in a flow, and it's subjected to different pressures, for example, and these different pressures may lead to a resultant force. This body may accelerate because of aerodynamic forces. And the elastic forces, the structure has a stiffness or flexibility, so the structure will deformate. And this subject is commonly treated in strength of materials disciplines, mechanics of materials. And when we have an intersection of inertial forces area and aerodynamic forces area, we have stability and control. Stability and control is dedicated to, there is a dedicated team. It's about how aerodynamic forces will interfere in the aircraft movement, aircraft rotational movement, pitch movement, roll movement. The deflection of the surfaces is involved. The intersection of aerodynamic forces area and elastic forces area is called static air elasticity. So this is mainly deformations of the structure caused by aerodynamic forces. For example, when we have a slender wing, different pressures Different forces will arise. We're going to have a resultant. This wing will deflect due to the air, due to aerodynamic forces. And inertia forces area and elastic forces area intersection is the structural dynamics. Structural dynamics is uh, sometimes it's referred to mechanical vibrations. The structure has stiffness and has an inertia, so it's going to oscillate, it's going to deflect um, due to these forces, and also the structure may have the damping. On this, we have elasticity. The structure will oscillate, will vibrate due to aerodynamic forces. Maybe some instability may arise, and also controllability of the aircraft. So this all together, this is dynamic air elasticity. Let's see more details about loads, specifically about loads. Um, Loads may be considered static when they are not time dependent. In this case, the aircraft is considered as a rigid body, and we have the action of inertia and aerodynamic forces. However, stability and control is not included in static loads technology. It's another part, another team that is responsible for stability and control. When we are working with static loads, analytical mechanics theory is applied and rigid body dynamics is applied. Sometimes it's necessary to work with different coordinate systems. So we must know how to dislocate and to rotate coordinate systems. All this theory is involved. Dynamic loads. When I say dynamic loads, I say loads that are time dependent. And as I've already mentioned, the structure is flexible and it has some inertia. And of course, it has damping because all structures have damping. And this is the theory of structural dynamics, sometimes called vibration. We have mode shapes, as you can see on the picture. A wing is vibrating, and it vibrates in very different ways, different shapes. We call mode shapes. Sometimes it's more convenient to work in the time domain because a dynamic load is a load that is time dependent. When I say that a load is time dependent, it means that the magnitude of this load is a function of time. For example, as you can see in the first picture, we have a load that roughly moving during time. So the aircraft response, the structural response is also a function of time. This equation, I believe everybody have already seen this equation. It's the equation of motion. We have the mass matrix, the stiffness matrix, first mass matrix, the damping matrix, the stiffness matrix. So we have inertial forces, we have damping forces, we have elastic forces, and all these forces are equal to the external forces on the right side of the equation. And sometimes it's more convenient to work in the frequency domain because when we have loads that are time dependent, we may work in the frequency domain because sometimes the structure will respond more in certain frequencies. Very, a very common situation is when the structure is in resonance. Resonance is when the structure has a peak of response in a certain frequency. So the second picture shows a frequency response. Some situations, for example, when analyzing a landing, it's more convenient to work in time domain, and the other situations, for example, system failures, it's more convenient to work in the frequency domain.